Hi everyone. For chapter 2, I'm actually going to try and fit everything into one video because I I looked through it and I just didn't see a real good stopping point. Um, a stopping point that wouldn't leave me with coming back and being like, hey, for 4 or 5 minutes, let me just talk about this real quick. So I'm just going to go through it all in one run, but you can obviously pause it and take breaks and all kinds of stuff. So in the previous chapter, we talked about the distributions of data. So this is data that you've actually collected, and it's going to probably be kind of noisy and random looking. In a probability distribution, what we instead have is a mathematically defined probability for each possible outcome. So with real data, we go out and we randomly collect values. We sample data points from the population of possible data points that we could have observed, and we end up with a sloppy, messy sample data distribution. With a probability distribution, we're saying without collecting any data, here's all the possible outcomes and here's how probable each outcome is. So the very simplest, well, maybe not the simplest, but one of the simplest probability distributions I can think of is the probability of rolling a 1, 2, 3, 4, 5, or 6 on a regular 6-sided die. Each outcome has something like a 16% chance of occurring. And when you add up the probability of rolling a 1, a 2, a 3, 4, 5, or 6, it adds up to 100%. There's a 100% chance that you'll roll at least one of these numbers. And you can cut up the area of this shape to say, well, what's the probability of rolling a 2 or lower? And that would be about a 2 in 6 chance, or a 33.33% chance. You can say, let's cut this shape in half, this little rectangle. Let's cut it in half and say, what's the probability of rolling a 3 or below? Equivalently, or equivalent probability would be, what's the probability of rolling a 4 or above? Anytime you add up the probabilities of adjacent outcomes, when you create an interval of outcomes and add up the probabilities in that interval, you're going to end up basically cutting out a piece of the total shape of the distribution. And within that shape, however much of the probability that you've cut out, the area of the shape, that represents the probability of observing outcomes within that interval. And that's really what's at the heart of hypothesis testing and statistical tests, is calculating the probabilities like these, except we don't use such simplistic probability distributions. See, like here, if you say the probability of rolling a 1 plus the probability of rolling a 2 plus the probability of rolling a 3 cuts the entire distribution in half. So you have half the area of the distribution highlighted, and that corresponds to a probability of a 1/2 or a 50% probability of randomly drawing one of these values off of the distribution. Normally, we're going to use distributions with more complicated shapes. Like these are pictures of the T distribution, which I go on more detail about in the chapter 2, but it's the same basic idea. With the 6-sided die example, every outcome is equally probable. With a T distribution, outcomes close to 0 are most likely. You might see something a little below 0 or a little above 0, but as you get further away from 0, those outcomes become less and less likely. The idea is still the same though. What's the probability of getting a 0 or higher? So in other words, if I make a random draw from this distribution, what's the probability of drawing something that's at least at a 0 or higher than that? Well, it's 50%. Just because the distribution can take on any value between negative infinity and positive infinity, it can be 0, it can be 0.01, it can be 0.5, it can be 0.51. That doesn't change the underlying idea that the area under the curve, or the percentage of the total shape that this area takes up, corresponds to the probability of drawing values from that distribution. As you get further and further away from zero, you end up with a shaded region where you say, well, if I'm randomly drawing values from this distribution, it's getting more and more unlikely that I'm going to get anything from this shaded area. And when I say drawing values randomly from the distribution, it's the same idea with the die example. When I roll a die, in a sense, I'm drawing values randomly. I'm going to draw a 1, a 2, a 3, a 4, a 5, or a 6 at random. Same with the t distribution. You're saying, I'm going to draw a number at random. It's probably going to be close to 0. Probably not exactly 0. It would be something like 0.13 or negative 0.12, so on and so forth. Probability distributions come with something called parameters. A parameter is something that governs the shape, where a distribution is located, how spread out it is, stuff like that. These equations might look scary. Don't be scared though, because we're not actually going to use them. The computer is going to crunch all these numbers for us. But the idea here is, like with the normal distribution up here, you need to supply it with an x. You say some value x somewhere on this normal bell curve, and say how likely is it to draw a value that high or higher, or between a -1 and a +1. It can give you that answer, but to really nail down what's the exact shape of this distribution, you also have to supply a mean, denoted by the Greek letter mu right here, and sigma, standard deviation, Greek letter sigma right here. You'll find those in the equation over here. The mean and the standard deviation need to be plugged into this equation so that we can know exactly how wide or how narrow the normal distribution is. When you change the shape of a distribution, you change the associated probabilities of any observations. So if I want to know what's the probability of drawing an observation at random between a -1 and a +1, that's going to depend. Is the mean 0? What's the standard deviation? Is the standard deviation 1 or is the standard deviation 15? That's going to change how likely different x values are to come up in the distribution. Another distribution that takes a parameter is the Bernoulli distribution. And I got an example of the Bernoulli distribution. Is also called the binomial distribution. I've got an example of the binomial distribution in chapter 2. The binomial distribution tells you, like, if I'm going to flip a coin n times, and the probability of getting heads, let's say, is p 50%, then how many coin flips are going to come up heads? And it'll give you a probability for each outcomes. And let's say I'm going to flip it 10 times, so n equals 10. The most likely outcome, if p, the probability of getting heads, really is 50%, then the most likely outcome, if I'm going to flip the coin 10 times, is that I'm going to get 5 heads. But if you've ever flipped a coin, you know that heads and tails don't come up exactly 50% of the time. You know, there's randomness to it. So you plug in the amount of times that you're flipping a coin, and you plug in the probability of getting a heads, you'll get distributions like these, which tell you how likely is it that you're going to get, let's say, 20 heads would be the middle of this blue one. Out of 40 flips, how likely are you to get 20 heads? The reason the binomial distribution is so important is not because people care so much about flipping heads or tails. It's that if you want to make statistical inferences, you have to have some sort of way of quantifying how likely or unlikely different outcomes are. So the example I use in the chapter is, let's say you're doing a clinical trial and you say, hey, when I do a placebo group with cancer patients, so they're receiving inert medication or treatments as a control group, usually within the time span of a clinical trial, about 5% of the people die during the trial. So that would mean if you took, 20 people in a clinical trial and the probability of dying is 5%, then the Bernoulli distribution will tell, or binomial distribution will tell you what's the likelihood of different amounts of people dying during the clinical trial for however many people are in it or how many trials you're doing for different probabilities. This is sort of at the heart of hypothesis testing with statistics, is you sometimes want to know what are these parameters. Like, so we know that in the control group, there's about a 5% chance of dying. Can we lower that to 2% if we're doing a new drug? Or with the normal distribution, you might have Beck depression scores. The most common score might be, I don't know, 35, 30. So the mean is normally 30, but you might say, well, I want to collect some new data where I'm doing something different and see if it's really 30. So it's kind of a question of which parameters do you plug in? What makes your data look more likely or unlikely? So here's an example unique to the lectures. Let's say the probability, so let's say you're the dean of education at a college. And so all of your graduates need to pass the praxis exam when they get out so they can get a job teaching. I think that's how it works. I should know because my mom was a high school teacher and all of her friends were high school teachers. I've heard them complain about all kinds of things associated with that profession, but somehow I missed it. Whatever. You're the dean of the College of Education, and 70% of your students pass the praxis on a given semester. And let's say you have about 50 students graduate every semester. Well, the binomial distribution will tell you, like, okay, if the chances of passing are 70%, so P equals 0.7, and you've got 50 people that are going to try and take it, binomial distribution says the most likely amount of people that are going to pass is 35. That's exactly 70%. But, we know about flipping coins and rolling the dice. You don't always get the population mean in your samples. Sometimes you're going to get 36 people passing. Sometimes you're going to get 34 people passing. In some rare cases, you might only get 25 people passing. That would be disastrous. But that's a very unlikely outcome. If this is the real parameter, if the probability of passing really is 70, you're probably not going to see only 25 people pass. Likewise, you're probably not going to see as many as 45 people pass, although that would be likely. Now, let's say you've been seeing this year in and year out, the same trend. It's always about 50 students, always about 70% passing. But you have a new instructor who comes in and says, I want to do this new experimental program that's going to really help the students pass the praxis exam. Well, you're a smart dean. You're not just going to invest all the money and time and let this new faculty member go crazy. You want to see proof that it probably actually works. So what are you going to do? You're going to apply. You're going to let them do a pilot program. Let's say they do the pilot program, and 37 out of 50, that's 74%, of students pass the praxis. Now, 74% is better than 70%, but you should know by now that when we're dealing with sampling error, sometimes you're going to see, even if no change has occurred, it still might be really 70% and the program did nothing, but we just happen to see a result that's within the realm of possibility. Coin flips, rolling the dice, random chance. Maybe they just happen to be a little lucky this time. If you ran the pilot study again, who's to say they might have a little less than 74%? Maybe they're only at 66% passing. So what we want to do is test the hypothesis. We say, what's the probability of getting 74% or better than 74% when you assume that there really is no difference? We're still at 70%. So you say, okay, what's the probability of 37%, 37 out of 50 when you assume this model, when you assume, okay, it's a binomial distribution, probability of passing is 0.7. The probability of 37 out of 50 passing, when you assume the binomial distribution and all that, is 10.5%. Okay. What about 38 passing? That's 8.4%. You keep going up from what we got, 37, and keep adding all of these probabilities together, and you're going to end up with, I can't read this, you're going to end up with a 32.79% chance. So when you assume that there really is a 70% chance and no changes happened, we're still back the way we were and this experimental program has done nothing. When you assume that's the case, there's basically a 33% chance that you would see people do as well as they did with the experimental program. So that's not very impressive. And we see this all the time. You know, people try things and they might see a little bit of success afterwards. That's not very strong proof, though. You would need to see either a bigger sample, because when the sample gets bigger, you can have a better idea of how likely or unlikely a small change is. But when you see such a small change, you know, we went from 70% success to 74% success, we can't rule out the possibility that this is just sampling error, that we just happen to get a little lucky this time. So a statistical hypothesis basically boils down to, you assume a certain model, right? And the one I just did, it was the binomial distribution with a parameter of 0.7 for the number of successes. You have to assume a certain hypothesis is true because you can't just calculate the probability of your data. You have to make an assumption. It's the probability of your data when you assume something. So what we do is we assume that things have not changed. In the praxis example, we assume, well, let's say that we're still at our normal 70%. When you assume that's the case, then you can calculate the probability of observing the data that you have. That's probably the heart, that's the heart of statistical hypothesis testing. You assume a certain model or a certain probability distribution is true. After you do that, you can calculate the probability of your data. One of the most frequently used distributions, I keep moving my face around, it's kind of weird. One of the most frequently used distributions for testing hypotheses in psychology is student's t distribution. And again, we got this big scary equation. We're not using this equation though. You plug numbers into this equation and it gives you one of these distributions. Now this is kind of weird. The normal distribution actually does change shape when you change its parameters. Student's t distribution has one parameter called degrees of freedom. And it starts off being wide when you have low degrees of freedom. So 1 degree of freedom is will make the t distribution shaped like this blue distribution right here. As you increase degrees of freedom, the peak gets taller and taller and narrower and narrower. And actually, once degrees of freedom gets really high, the whole thing is just the normal distribution. What the t distribution represents is, let's say, the probability of a difference between sample means. Like if I have a control group versus an experimental group, or I have honors students' self-esteem versus non-honors students' self-esteem. The difference between means, you say, let's assume that there is no difference. That's the null hypothesis. And then once you make that assumption, you go to the t distribution. If you're assuming that a difference between means is the most likely outcome, so 0 is the most likely outcome, you want to know, did I observe a big enough difference between my means to where I'm cutting off a very small piece of this distribution? If you cut off a very small piece of the area under the curve, that corresponds to a low probability of observing that data when you assume your hypothesis is correct, that there is no difference. So it's kind of backwards with null hypothesis significance testing. You assume you're wrong. Once you've made an assumption, you can then calculate the probability of your data. And once you've done that, you can say, well, the null hypothesis, the hypothesis that I'm wrong, there is no difference between groups, must be wrong because I know my data is correct, but my data are unlikely when you assume the null hypothesis is wrong. I mean, when you assume the null hypothesis is true, then my data end up having a low probability. So we reject the null hypothesis. Another popular use of the T distribution is for correlation coefficients. If you have a correlation between two variables, if you have no correlation between two variables, meaning variable 1 tells you nothing about variable 2, they're unrelated, that would be a correlation of 0. As the correlation between two variables increases, though, there's more a sense in which as one goes up, the other one goes up too, or tends to go up, or as one goes up, the other one goes down. That corresponds to a positive correlation or a negative correlation. If you assume, if you have a hypothesis, I think that there is a correlation between these two variables. I think self-esteem is correlated with closeness with your parents. You know, you go and collect those variables, you calculate your correlation, and first you say, okay, I want to calculate the probability of my data. You cannot go directly to doing that, though. There has to be some assumption. So we assume the null hypothesis is true. We say the correlation between these variables is 0. That means if that's true, then the most likely outcome is that you'll see 0 correlation, but you'll see a negative correlation or a positive correlation. If the null hypothesis is true, you'll be close-ish to 0, but random chance, it's not going to be exactly 0 every time. If you observe a correlation that's small enough or large enough, then you'll be able to say, hey, according to the null hypothesis, the probability of observing a correlation as large or larger as the one I did is like less than 5%. That means the null hypothesis must not be true. So far I've been talking about one-tailed statistical tests. That's when you think that some effect, like a difference between means or a correlation, is higher than 0 or lower than 0. And you actually, this is a better visualization of it. So this is a one-tailed test. So you assume there's no difference between the means, or you assume that there's no correlation. Your real hypothesis is that there is a difference between the means, and there is a correlation. But it's in what we call null hypothesis significance testing, we can't really go directly to calculating the probability of our data. We have to assume some sort of underlying distribution. So in a one-tailed test, which is what I have been talking about, you say, okay, suppose there's no correlation, suppose there's no difference between means. Now, if I happen to observe a difference between means or a correlation or whatever the effect is, if I observe an effect so large that it surpasses the top 5% of the area under the curve, that means that there's less than a 5% chance of observing the data that I did, or more extreme data, when you assume the null hypothesis is true. That's a one-tailed test. We just got to get past the top 5% of the area under the curve. If you flip this around and you say, I think there's a negative correlation, then if you observe a negative correlation so large in magnitude, so it's so negative, so far away from 0 in the other direction that it cuts off the bottom 5% of the area under the curve, or more than the bottom 5% of the curve, like the bottom 2% or the bottom 1%, and you can say, well, I'm going to reject the null hypothesis because when I assume the null hypothesis is true, my data are very unlikely. And we know that we have our data. If one's got to go, our data or the null hypothesis, we're going to get rid of the null hypothesis and assume that the null hypothesis is false. That's a one-tailed test. A two-tailed test is when you don't predict a certain direction for the effect. That's when you say, there is some correlation. I'm not going to necessarily predict that it's positive or negative. Or if you say, I got these groups, one of them might be higher than this other group. You know, STEM majors might be higher in self-esteem than non-STEM majors or whatever. I'm not necessarily predicting a certain direction. When you do this non-directional or two-tailed test, because there's two tails of the distribution, what you do is you split the 5% in half. If the top 2.5% up here, you have the bottom 2.5% down here. And you've moved the goalposts and you say, well, I need to get into the top 2.5% to reject the null hypothesis, or I need to get into the bottom 2.5% to reject the null hypothesis. This is harder to do. And back in the day, you were allowed to say, look, I predict that there's going to be a positive correlation, or I predict this group is going to be higher in self-esteem than this group. When you predict a direction, it's easier to achieve statistical significance. Well, psychology has gone through a lot of controversies, a lot of methodological controversies. And nowadays, if you're reporting your results and you say, well, I observed a statistically significant result, you know, the probability of observing my results when you assume the null hypothesis is true is less than 0.05. Therefore, I reject the null hypothesis. According to a one-tailed test, that's when alarm bells go off. And people say, oh, a one-tailed test. Well, what happens when you do a two-tailed test? Because you could be pulling a fast one on us. You may have had no idea what direction the results would go in, but then you got the results and you said, I don't quite get into the top 2.5%. I don't quite get into the bottom 2.5%. If I just move myself over, like, oh no, I wasn't doing a two-tailed, I was doing a one-tailed. Now it's statistically significant, because before, when I was doing a two-tailed, I had to get over here, moving the goalposts. So that's why it's kind of assumed by default these days that you're doing a two-tailed test. You have to observe a result that's higher than the top 2.5% or lower than the bottom 2.5% when you assume the null hypothesis is true. You have to observe that extraordinary of a result according to the null hypothesis. They're going to assume you're doing a two-tailed test. And that's what statistical significance is. When you say the results were statistically significant, that means that when you assume the null hypothesis is true, your data are incredibly unlikely. Therefore, you can assume the null hypothesis must not be true. When you reject the null hypothesis, you know, and that, let me back up. A p-value, you see p-values, p less than 0.05, that means the probability of my data are less than 5% likely when you assume the null hypothesis is true. That's what a p-value is. And when p is less than 0.05, we say the results are statistically significant. Now, we have null hypotheses, which basically say, I'm wrong, there's no correlation, there's no difference between groups. And we have the alternative hypothesis, which is that there is some difference between these groups. There is some correlation between these two variables. You could even do a directional version or a one-tailed version of those and say, I think there's specifically a positive rather than negative correlation, or I think specifically that group A is larger than group B or group B is smaller than group A. Those are alternative hypotheses. When you reject the null hypothesis, you're not really providing evidence for the alternative hypothesis. You're only making the null hypothesis look implausible. So you're basically just saying there's not nothing, okay? That might seem like that's good evidence of something. I said there's not nothing, that means there's something. And you're not wrong for having that intuition. It's just that you should really look at the size of the effect once you reject the null hypothesis. That tells you that there's not nothing, but that doesn't tell you necessarily that there's like a meaningful difference or a meaningful correlation. It might be such a small difference or such a small correlation that you manage to get statistical significance, but it doesn't really have any practical value. We'll elaborate a little bit more on that in the next couple of slides. Yeah, when you collect data, you assume the null hypothesis is true for the sake of argument, and then you calculate the probability of your data, or more extreme data, because this is an interval of data. All you have is your data and your p-value. You don't have direct knowledge of whether the null hypothesis is true or false. So you could be making a mistake when you reject the null hypothesis or retain the null hypothesis, fail to reject, retain, tomato, tomato. And I'm actually going to go to a different slide to talk about type 1 errors and type 2 errors. So you don't know if the null hypothesis is true. You don't know that there's no effect. You assume it's true so you can calculate the probability of your data. That's where the p-values come in. But you never know exactly whether it's true or not. So let's say, hypothetically, unbeknownst to us, the null hypothesis is true. There's no correlation, there's no difference between groups. Despite that, Lady Luck played a trick on you. You happen to get some data that's very extreme. Extreme data does happen, you know. Technically, it is possible to flip a coin 10 times and get heads every time, or roll a dice 10 times and get a 6 every time. It's not likely, but it can happen. Well, you assume the null hypothesis is true, and then you observe some extraordinarily rare event that made it look like the null hypothesis is false. So you reject the null hypothesis. This is called a type 1 error. You rejected the null hypothesis, but the null hypothesis is true. So you're kind of, scientifically, this is like you saying, ah, there's something there, there's an effect, when there really is no effect. Now, if the null hypothesis is true and you collect your data and the data just look like, yeah, there is no correlation, there is no difference between the groups, so your p-value is not very low, then you say, okay, well, I cannot reject the null hypothesis. I'm going to retain the null hypothesis. You're all good if that happens. That's not an error. Similarly, if the null hypothesis is false and there is an effect, well, that means that if you collect data, if you collect enough data, you should see like, hey, my data the effect that I observed in my data is too large, such that if you assume the null hypothesis is true, then my data just looks very improbable. There's less than a 5% chance that you'd observe data as high or higher as the data that I observed. So I'm going to reject the null hypothesis. Well, in this scenario, the null hypothesis was indeed false. So you rejecting it is good. That's what you should have done. No errors there. But let's say there is an effect. So the null hypothesis is indeed false, but you don't get data that speaks to that. Your data says, no, the null hypothesis is true. It looks like there is no effect. That's called a type 2 error. That's when there is an effect, but you retain the null hypothesis. You failed to reject the null hypothesis. The null hypothesis was false. You should have rejected it, but you didn't. What's going on here? This is an image I saw, I forget where, but it was a pretty good illustration of the dangers of type 1 errors and type 2 errors. When you get a type 1 error, it's like you're saying there's something there. The null hypothesis is false, but that's kind of a false positive. You're like this situation right here on the left. You'd hate to go and tell everyone, hey, I think I have an idea for how we can treat depression or how we can help kids with career counseling or whatever services you're providing based on a false positive, a type 1 error. So type 1 errors are pretty bad. Type 2 errors are pretty bad too, because you're saying there's nothing there when there actually is something there. You're like the person on the right here. So imagine if there actually is something you almost discovered. you almost discover that there is this way to help people with anxiety. There is this way to predict who's likely to, uh, you know, fall back into, they go to rehab, they overcome their drug addiction, but some people will relapse, and you have a way of predicting who will relapse and intervene on that. But your data weren't extreme enough to establish that. You didn't see that effect, so you just assumed, oh, well, maybe I was wrong. That's a type 2 error. If there was something there, you weren't wrong, but you didn't get the data that you needed to show it. That's a type 2 error. That's a missed opportunity. All of this stuff is very related to the idea of statistical power. Statistical power is the ability of a study to detect an effect when that effect is real. In other words, it's your ability to reject the null hypothesis when the null hypothesis is in fact false. There are a bunch of things that affect statistical power. The most important things are sample size and effect size. You have control over sample size. And in psychology, many of the effects that we look at are actually pretty small. The correlations between stuff like self-esteem and self-efficacy, or the correlation between how left-leaning or right-leaning you are politically, and how much does that correlate with like how much money your parents made growing up. Psychological things like that, there's just a lot of noise, and so the correlations are never quite that strong. So you need a very large sample in order to detect something that's that small. On the other hand, if the effect is large, you don't need that large of a sample to detect it. And you normally can't control effect size. If you're hypothesizing about political psychology or about depression or about school counseling, stuff like that, you're stuck with the effect sizes that actually exist. You don't go picking studies based off of what's most likely to be easy to detect. I use the example all the time of, if I think there might be a correlation between drinking diet soda and height, like I think people who drink more diet sodas per day are shorter. If that effect exists at all, it's going to be so small, and you'd have to collect tens of thousands, maybe hundreds of thousands of observations to have any chance of even seeing that come out. On the other hand, if I think people bowl better whenever they're in a normal state versus when I've sprayed them in the eyes with mace. You spray people in the eyes with mace, they're not going to bowl as well. So you'll see a statistically significant difference between their bowling scores, between when they had mace in their eyes and when they didn't have mace in their eyes. That would be a big effect size. You wouldn't need but maybe 6, 8, 10 people, and you'd get a statistically significant result. But again, you don't usually pick studies based off of how big the effect is. Although you should think about what size of an effect would actually mean anything in this study or in this context. This stuff can get really complicated, but really interesting. I recommend this book, Science Fictions by Stuart Ritchie. Statistical power is one of the topics that has lent to what's called the replication crisis or the methodological crisis in science. I don't like to think of it as a crisis. We've already known about these issues for a long time. But basically, some people do some not so great things with their data analysis, and these ideas of statistical power and type 1 errors and type 2 errors and how we can end up wasting money and wasting resources or missing opportunities is all very interesting stuff, and it's stuff we need to learn for this class. But if you want to learn more, I really suggest reading this book. It's pretty good. I'm going to end off real quickly talking about confidence intervals. I'm not so much concerned in this class for how to calculate confidence intervals. A lot of times when you use a statistical program, it'll calculate that for you, assuming you tell it the right kind of parameters, like, is this a normally distributed variable or is this a a correlation. If it's a correlation, it's going to use a different equation to estimate the confidence intervals. But basically what a confidence interval does is it says, okay, you observed, let's say, a difference between groups of this big, you know. But, you know, because sampling error is the thing, you might have, you know, next time you run this study, you might have observed a difference that's not this big, it might be only this big. Or you might observe something bigger. That's sampling error. So a confidence interval, loosely speaking, this isn't the technically correct way of conceptualizing what it's doing, but in a way, what a confidence interval does is it says, this is the effect size, this is the size of the effect that you saw, but given the size of your sample, it could have been this low or this high. So the lower boundary and the upper boundary kind of give you an idea of the range of possibilities. You saw a result that's here this time, but next time it might be somewhere over here. And a confidence interval will change from sample to sample. Let's see, I think I have a graphic here. Yeah. So let's say the mean, the real mean, denoted by the Greek letter mu right here. Let's say the real mean is right here. So when you collect a sample, you have a confidence interval where the upper bound is the mean might be somewhere over here. You don't know where the real mean is. You say it might be somewhere up here, might be somewhere down here. Your sample estimate is going to be in the middle. So if the middle of your interval is right here, that means you missed the real value by just a little bit. And the confidence interval will say, yeah, you observed it right here, but I mean, it might be down here or up here. And if you keep drawing new samples, trying to estimate where the population parameter is, the middle of your confidence interval will change. It'll jump around as you might expect. You know, sampling error, you're not going to see the mean, the population mean every time. You're going to see underestimations and overestimations from time to time. But if you spread out and say, look, you know, for this sample right here, I got my estimate of the population mean, my sample mean is right here. But each time I'm going to say, well, I mean, it's right here in this sample, but it might be as low as this or as high as this. As you can see, every time you draw a 95% confidence interval, the interval usually contains the population parameter in its bounds. In fact, 95% of the time, it has the real population parameter in its bounds. What's going to happen 95% of the time, or 5% of the time, sorry, that's once out of every 20 samples. You might be the unlucky person who collected a sample and said, I think the mean is here, and you missed it, even with the confidence intervals. I talk more about that in the chapter. Well, what the real takeaway I want you to have with confidence intervals is that it's kind of like a p-value in the sense that if I say that you know, the correlation is 0.15, but it could be as low as 0.01 or as high as 0.21, that's a pretty wide margin. And the lower end, 0.01, is very close to 0. So you have this wide 95% confidence interval, and you just barely got away from that 0 mark. If 0 had been within your interval, like one boundary is positive and one is negative, that means that 0 is somewhere in the middle. That would mean that you couldn't reject the null hypothesis because you can't rule out 0. 0 being no difference between means, no correlation between the two variables. But if you have a confidence interval where both of the boundaries are below 0 or above 0, and they're pretty narrow, like let's say I collect a sample, I got a correlation of 0.15 between two variables. And it could be as low as 0.14 or as high as 0.16. That means, you know, you'd have to have a really big sample to have a 95% confidence interval that's that narrow. You can see from the confidence interval that it's real narrow. Like I got a 0.15, but the range of possible values are very concentrated at a certain point. And you didn't just narrowly escape the 0 point, you're very well secure away from the 0 point. So confidence intervals tell you everything you get from a p-value, because a p-value is kind of two sides of the same coin. A p-value tells you whether you can rule out the null hypothesis, the 0. The null hypothesis is that there's no correlation between these two variables. There's no difference between these two group means. Your 95% confidence interval is like, okay, what's the correlation? What's the difference between groups? You find your estimate of that difference, that effect size, that correlation, and then you say, okay, if I widen that out to like, what are the range of possibilities given my sample size? The confidence intervals tell you if 0 is within the boundaries, then you cannot reject the null hypothesis because 0 is within the realm of possibility. But if it's out, that means, yeah, it's probably not 0. In addition to giving you that sort of yes, no, statistically significant, not statistically significant, confidence intervals also tell you, like, is it a narrow confidence interval or is it a wide confidence interval? Because if it's a wide confidence interval, probably from a small sample, that means, you observed an effect that's this big, but really it could be next time you run this. Small samples are very erratic. They're crazy. They're really big and really small means, correlations that are really big or really small. You can't really depend on them too much. They're very erratic and have lots of random noise in them. So confidence intervals give you that added information, how much confidence you can have in what your actual effect is. So that was a lot to take in. And if you're like most of my students, you need to go over this again because this is some heavy stuff. So if you watch this and you're feeling a little confused, that's completely normal. I recommend reading chapter 2 at least twice and being an active reader, because this is the foundation. Everything that comes after this, we're going to start talking about how to actually do the t-tests and how to actually do the correlations. This is all the stuff I'm just going to assume you understand by now. So really make an effort to really get this stuff. And if you're not getting it, feel free to email me. I'm very good about creating supplementary material or clarifying things. So don't hesitate to reach out. All right, I'll see y'all next time.